with the bearing capacity of the shallow foundation, and we will discuss the ultimate bearing capacity, that what is the ultimate bearing capacity of the soil and how we can define that. Then when we load a soil, depending upon the type of the soil or the state of the soil or the condition of the soil, the failure mechanism or the mode would be different, and there would be different modes, for example, general, local, and punching shear failure. Then there are a few terms which are very important and which will be used practically in examples and problems as well. So, what is the gross pressure intensity? Don't confuse yourself with the pressure intensity. So they are interchangeably used with the bearing capacity. So it's the gross bearing capacity, net bearing capacity or the pressure intensity, safe bearing capacity, and allowable bearing capacity. So these are the terms which will be discussed and explained in coming few slides. Now, obviously, if you want to find out the bearing capacity of a soil, there should be methods to find out the bearing capacity determination. Now, for bearing capacity determinations, there are few methods. For example, analytical methods, that we will make few assumptions, and based upon these assumptions, we will come up with the bounds methods, where we will have a lower bound theorem, we will discuss upper bound theorem, and we will also discuss the limit equilibrium method, which we already touched a little bit on the limit equilibrium, and in fact in detail in the landslide slope stability chapter in Geotech 2. Then we will discuss in very good detail a very important theory which is used for finding the bearing capacity of the soil, and that is Terzaghi's bearing capacity equation, and the failure mechanism and the derivation of that equation will be discussed in greater detail. Then we will discuss the effect of water table on the bearing capacity of the soil. Rest of the topics will be discussed in the next week. So this is just an overview that what we are going to expect in our today's lecture. Now, starting with the chapter 2, which is bearing capacity of the shallow foundation. Now, what is an ultimate bearing capacity? For example, here we are given with a ground surface, and if we construct a foundation beneath the ground surface, load would be applied, and that load will apply some pressure, which can be Q ultimate load per unit area. And that soil, for example, if I say this is the boundary of the soil, will try to bear the pressure which is exerted by the foundation onto the soil. So that property of the soil, or the least pressure which can cause the shearing failure, and this soil, then we will discuss in greater detail in a few minutes, that there will be kind of a shear failure which will occur beneath here in this, on this side as well. So kind of a shear failure will occur so the least pressure which will cause the shear failure is known as the ultimate bearing capacity of the soil. So here's the definition. If you want to define more appropriately, the least pressure which would cause the shear failure of the soil immediately below and adjacent to the foundation, that is known as the ultimate bearing capacity. And if you remember, we discussed in the previous introductory lecture that whenever we are designing a foundation, that is dependent upon the two criteria, which is the shear failure criteria and the settlement failure criteria. And settlement was equal to 25 millimeter or 1 inch. So the least pressure which would cause this shear failure criteria to occur, that is known as the ultimate bearing capacity. Now, there are different modes of shear failure. For example, general shear failure, local shear failure, and punching shear failure. Now, for general shear failure, let's go here. Going down. Yeah, that's good. So in case of general shear failure, for example, if we place a footing here, and this is the ground surface, so here is the footing, and a load is applied on top of that footing, there are three zones which will be developed. For example, the elastic zone or the elastic wedge, then there will be a radial zone, and you can call that as zone 2, and there is another linear zone here and on this side as well, and that is known as the Rankine passive zone, which will be discussed in Terzaghi bearing capacity equation. Here we can see bulging or the heaving of the soil. So in case of general shear failure, you will clearly see that wedge, the slip surface, and also the heaving of the soil. If we want to draw the pressure versus settlement curve, now in that case, we will slowly move towards the peak load, and suddenly we will have a well-defined failure load or pressure, you can call it failure pressure. Now this type of shear failure will occur in case of dense or stiff soils, and as we mentioned, well-defined failure load will occur. Now that sudden collapse will occur in case of general shear failure. Now there is another type, which is the local shear failure, and in case of local shear failure, we will be having a wedge, which is the elastic wedge, and slip surface, and partially we will see these heaving or bulging phenomena, but it's not prominent in case of the local shear failure. Now this will occur in high compressibility soils. The failure load is not well defined, so the failure load is not well defined. I would call that well defined. In this case, large settlement will occur. Settlement will occur. What else? And here, in case of the general shear failure, tilting will occur, but no tilting after the sudden collapse. Okay. Now, in case of, let me take another color. I will take the blackish one. So, in very high compressibility soils, we will experience a failure mode, which is punching shear. Okay, punching shear failure. So here we can clearly see that only wedge can be seen in this kind of failure mode, and we can clearly see here that the ultimate load would be very low compared to the local shear failure and for the general shear failure. Now significant settlement will occur. Large settlement will occur in this condition as well. And as I mentioned on that in very high compressibility soil, this kind of shear failure mode will occur. No bulging, no tilting of the footing will occur in this type of failure mode. Please confirm that you can hear me and the screen is visible.
Yes, sir.
Yes, sir.
Okay, thank you very much. Those details are also mentioned here. If you are interested, you can read that as well. And here, if you want to draw combinedly and if you want to compare, or if you want to draw in such a way which will make things a bit more clearer. So if this is the settlement, sometimes I don't know, the pen is getting stuck here. So it's the pressure here. So this one will be the general shear failure. Now, this one will be the local shear failure. And now in case of the very high compressibility soil, this one will be bunching shear failure. And different zones for the dense or stiff soil, I would say high compressibility soil, very high compressibility. So this is the general shear failure mode, local shear failure mode, and the bunching shear failure mode. Now there is another explanation is given on that was related to the cohesive soil. Now how we can relate the modes of failure with the density or relative density which is related to the cohesionless soils. Now, the term relative density is used here again. So I would say, what is relative density? Anyone?
Sir, density of any substance to the density of reference material.
So if you remember, we studied that in Geotech 1 as well, and I think in Geotech 2 as well, but mostly in Geotech 1, that what is relative density? The hint is that we are relating it with the word ratio. And obviously we are comparing it with a reference, and that reference is given in that equation, or was given in that equation, I would say. And if I write that equation, you will remember that what I want to say. So it's the E minimum, E max minus E, and E max minus E minimum. This is the maximum void ratio. Here is the minimum void ratio, and this maximum void ratio will give us the minimum density, and this minimum void ratio will give us the maximum density. Okay, and this E is the field void ratio. Anyways, that was just to refresh your mind on the relative density term which is used here. Okay, this is here. I think that's much clearer now.
सर ये इमैक्स और मिनिमम भी समझाएं रिलेटिव डेंसिटी.
क्या जी?
ये रिलेटिव डेंसिटी में जो मैक्सिमम वाइड रेशियो है और मिनिमम वाइड रेशियो.
मैक्सिमम वाइड रेशियो सबर करें, ये क्वेश्चन किसका है? क्वेश्चन किसने पूछा है?
सर मैंने तौसीफ जुनैद.
अच्छा, तौसीफ जुनैद. ई मैक्स ई मिनिमम हमने जियोटेक 1 में पढ़ा है.
पढ़ा था सर,
याद आए?
पढ़ा था
हाँ,
लेकिन अभी
बिल्कुल याद नहीं है. ये तो मेरा क्वेश्चन है, ये तो मेरा आपसे क्वेश्चन है कि ई मैक्स और ई मिनिमम क्या होती है. और मैंने बताया कि ई मैक्स जो है ना, आपके पास मैक्सिमम वॉइड रेशियो होता है जिसमें सबसे ज्यादा वॉइड्स प्रेजेंट होते हैं. ठीक है, और सबसे कम वॉइड्स जो प्रेजेंट होते हैं वो होगा ई मिनिमम. इसी को हम रिलेट कर सकते हैं डेंसिटी ऑफ द सॉइल. अगर हम डेंसिटी ऑफ द सॉइल के साथ रिलेट करना चाहते हैं तो अगर हमारे पास वॉइड रेशियो मैक्सिमम होगा तो क्या ये हमारे पास मैक्सिमम डेंसिटी होगी या मिनिमम डेंसिटी होगी? ये जवाब आप दें.
सर मिनिमम डेंसिटी होगी.
ऑब्वियसली. ठीक है, तो ये चीज मैंने बताई कि ये हमारे पास रिलेटेड होता है मिनिमम वॉइड रेशियो के साथ, हमारे पास सॉरी मिनिमम डेंसिटी के साथ रिलेटेड होता है, क्योंकि हमारे पास ई मैक्सिमम है. फिर जब बात आती है हमारे पास Ashad Zawar, please stop texting in the chat box. अब जब हमारे पास यहाँ पे E मिनिमम होगा तो ये हमारे पास मैक्सिमम डेंसिटी होगी या मिनिमम डेंसिटी होगी? तो सिर्फ
सर मैक्सिमम डेंसिटी होगी.
क्यों?
सर क्योंकि वाइड्स कम होंगे ना तो ऑब्वियसली डेंसिटी ज्यादा होगी ना, इसका मतलब है.
अच्छा, तो वर्ड्स कम होंगे. वर्ड्स क्यों कम होंगे?
हमने इसको कंपैक्ट किया हुआ है ना.
एग्जैक्टली. ठीक है ना, जो कंपैक्शन हमने जियोटेक 1 में पढ़ी, तो ये उसके साथ रिलेटेड एक डिस्कशन मेरे जहन में आई कि मैं करूँ. ओके, सो if the relative density is greater than, I would say, for example, 35% or less than, I would say here. Now let's start with the punching first. So we will experience the punching shear failure. Now in between 35 to, I would say, approximately 70%, if the relative density is in between, or we can also write for loose sands and for medium dense sands and very dense sands, we will experience general shear failure for the relative density greater than 70%, and in between, or for the medium dense sands, we will experience the local shear failure mode. So these are the three failure modes which we can relate to different types of densities of the, or even the state of the soils as well, if it is depending upon the compressibility or if it's related to the density or relative density of the sand or cohesionless soils. Now that was related to the mode of shear failure. I have a video to show you, just to explain a few things. Can you hear the voice? Please confirm.
No, sir.
Okay, the voice is not clear. Let me see. How about now? Is the voice clear? Please confirm about the voice. Is the voice clear?
No, sir.
Okay, so you can. I will explain in English so that. So when we construct a house there, loads will be applied and the pressure will be exerted onto the soil. There are different types of shear failure modes. Basically, it's self-explanatory as well. You will have a punching shear failure mode, and in that case, we will only have a wedge-shaped structure. And the demo has been also shown in here that you won't see heaving, but the foundation is going deep. Significant settlements are occurring. Now we move towards the local shear failure mode, and you can clearly see that the well-defined wedge and slip surfaces are the radial zones are present. And if you want to have the demonstration, you can also experience settlements there. But when we go for the general shear failure, we can clearly see heaving or bulging, and significant tilting can also be observed in case of the general shear failure mode. Now there are different types of failure which occurred due to the bearing capacity of the soil. So silos where we keep the grains in Manitoba, Canada, that was significantly underestimated the bearing capacity and also underestimated the load. In fact, overestimated the bearing capacity and underestimated the load which was acting on top of that silos. There are different types of solutions which can be appropriate to tackle the shear and the settlement failure criteria. For example, mat foundations can be constructed beneath the foundations or for beneath the structures there. Pile groups can be an option, which will be discussed in chapter number 4. Different types of techniques can be applied, for example, aggregate piers, grouting, soil mixing. If you remember, we had a good presentation on the compaction characteristics as well. So we can also apply all these methods to increase the bearing capacity of the soils. Now, coming back to the general terminology which will be used.
Excuse me, sir. सर अगर हमारे पास relative density of the soil same हो ना किसी project के लिए तो फिर mode of failure depends upon the applied load इस तरह होगा सर.
So see, Junaid.
Yes, sir.
Please repeat the question in English.
Sir, if the relative density of the soil is same, so then mode of failure, whether it will depends upon the force or again it will depends upon the soil density.
Obviously, it will be dependent upon many factors. The loading will also play a significant role there, and the soil condition will also play. These are just an approximation that are provided to give you an idea, a rough approximate idea that how the soil will behave if the soil is highly compressible or very high compressible. The loading will definitely play a significant role in there as well. But based upon the soil condition, I would again say that based upon the soil condition, we will mainly see these type of failures.
Okay, sir, got it. Thank you.
Okay. Okay, we will have a question and answer session at the end of the lecture. So please hold on you can write down those questions there so that we can finish the lecture within the specified time. Okay. please. Now, there are few terms which are used in finding the bearing capacity. For example, the gross pressure intensity or the gross bearing capacity. So if we add the weight of the superstructure, for example, the weight of the superstructure, weight of the foundation, weight of the backfill soil, and if we add these three and we divide that by the area, we will get the Q gross or the gross bearing capacity of the soil. Now, here is an illustration that how we can find out this is the superstructure, this is the weight of the foundation, and here the backfill soil is also applying load. Here is the area, we call it the B. Now the net pressure intensity, which will be used in solving the example problems. So this is the equation. Please kindly note down this equation as well. It's a very important equation to find out the net bearing capacity. You can also note down this equation. These are used in solving examples and problems. Okay. Now the net bearing capacity or the pressure intensity, if you simply subtract, this is the Q gross, which is obtained by from the weight of the superstructure, weight of the foundation, weight of the backfill soil. Okay. Now you need to subtract the gamma into D, or this soil. For example, this one is the depth of the footing, and we are having a unit weight of the soil. So gamma into D, I would call that as Q. So if we subtract or we remove this soil from the Q gross, because in Q gross it was included. Okay. Now if we subtract this portion, which is gamma into D, we will obtain the Q net, and this is now. For example, there are a few assumptions which we can also make, that for example the weight of the foundation is roughly equal to the weight of the backfill soil. Now then this will be equal to the gamma into D, and we can say that the Q net or the net bearing capacity will be equal to the weight of the superstructure divided by the area of the footing. But we will use this equation in samples and problems. Okay, now there is a safe bearing capacity, and for the safe bearing capacity, this is the equation which you need to note down, which will be used in solving examples and problems. Now we need to divide the ultimate bearing capacity by a certain factor of safety, and we had a discussion related to the factor of safety, that why we apply factor of safety in designing the foundation in the previous introductory lecture. So we already know that there are lots of uncertainties in the loads and also sample collection testing, etc., or even the temperature variation or moisture fluctuation, okay, weather conditions, okay, so these are, etc., etc., you can say these are the uncertainties which we are not sure about. So if we are not sure about, we apply that factor of safety, which will ultimately increase the dimensions of the foundations. But still, we need to be safe. The structure needs to be safe. Therefore, we apply a factor of safety. Okay. Now that factor of safety will be known as the safe bearing capacity. Now for the case of allowable bearing capacity, now there are different terms because we can also find out the net bearing capacity. For example, if you are dividing the ultimate bearing capacity divided by the factor of safety, so we are getting the Q safe, I would say here Q safe, and if we subtract the gamma into D, for example this one will become Q ultimate minus gamma into D, and that would be Q ultimate net. Okay, so if we subtract this term from the ultimate, and that will become the Q ultimate, and if we divide it by the factor of safety, and the factor of safety is usually taken 2.5 to 3, so we can find out the Q safe net. Now what is an allowable bearing capacity? So it's the maximum pressure which may be applied to the soil such that the two fundamental requirements are satisfied. This will give us the limiting settlement and the shear failure criteria. Now the allowable pressure is the minimum of Q safe and the stress which is required to cause a specified amount of settlement. So the minimum between these two, Q safe, which is obtained from the Q ultimate divided by the factor of safety, and the stress which will be studied in the settlement lecture, that how we will find out this bearing capacity. So the stress required, or we can call that as a stress which is required for 25 millimeter or 1 inch settlement. So the minimum of these two is known as the allowable pressure. Okay, the allowable pressure or the allowable bearing capacity is the minimum of these two criteria. Now, methods of bearing capacity determination, we will go in very good detail for this method of the Desargues bearing capacity equation today. The Meyerhof method, Hansen method, these methods are analytical methods to find out the bearing capacity of the soils. There are various correlations which are also proposed by various researchers to different field tests. For example, the standard penetration test and the cone penetration test to find out the bearing capacity of the soils. In Geotech 2 lab, you might have performed the plate load test and pile load test to find the bearing capacity of the soils. There are various presumptive bearing capacity or the recommended bearing capacity codes proposed by various countries, various societies to find out the bearing capacity of the soils. These three topics we will cover in our course. this one, the fourth one, we might not be able to cover in our course. Now, we will briefly go on the analytical methods, that how we can estimate the bearing capacity. And then we will end up with a slightly complex way, and we will go in detail that how we can use the cohesion and the friction angle to find the ultimate bearing capacity. So for the start, we will discuss bound methods. And for the bound method, there are two types of bound methods. One is the lower bound method, and the another one is the upper bound method. Now, in simple wordings, if we have a true failure load, and if we obtain the lower bound solution, okay. So if we obtain a bearing capacity from the lower bound solution, this will be less than the true failure load. Now, to calculate the lower bound, we must satisfy the condition of the equilibrium, or we can say the shear failure, and we don't worry about the displacement or the compatibility of the system. Now, very simple way to find out the bearing capacity of the soil, that we can take phi equal to 0, and we can take the example of a strip footing. So you can clearly see here that we are making assumptions, and very simple assumptions, that for a strip footing and for a cohesive, purely cohesive soil, how we can find out the bearing capacity. Now here is a foundation. This is the ground surface. This is the foundation here. The load is applied, P ultimate, and the pressure is applied on top of that footing, which is the Q ultimate. So at a state of plastic equilibrium, we will mark this line here, and we will take two elements, one from this zone and the another element from this zone. Now at the point of plastic equilibrium, we will find out the stress conditions at different locations. Before going there, please note down that the overburden pressure is Q bar is equal to gamma into D. Now, sigma 1 and sigma 1 will act at the major principal stresses, major principal planes, and sigma 3, which is the minor principal stress, which will act on the minor principal planes. Now, as the ultimate load is applied on top of this element, there will be a horizontal component which will be transferred. For example, here I would say that if the stress is applied, that stress will be also transferred in the horizontal direction here, and the horizontal stress will be equal to on the one element number 1 and element number 2. So here sigma 3.1 is equal to sigma 1.2, and sigma 3.2 will act on the, and this one will be the major principal plane because this stress would be greater than this one, and I will explain why. Because only gamma d is acting here and q ultimate is acting on this plane, and this is going to exert the horizontal stress onto this plane, which is the major principal plane, and here is the minor principal plane. Now this is the important point to start with. Remember from Geotech 2, from triaxial test also, and from the Mohr Coulomb failure criteria as well, that if this is the tau, if this is the sigma, this is the Mohr Coulomb failure envelope. If you draw a Mohr circle here, this will be sigma 3, and here we will have a sigma 1, and this one is the delta sigma d, which is the deviator stress, and this is the C cotangent phi here. Okay, now, and if we want to compare the sigma 1 and sigma 3, or which are the major and minor principal stress, so we can write that equation here, but we already know that phi is equal to 0 and tangent square 45, that would be equal to 1. So this would be, I guess, equal to 1, I would say. So it's 2c here, and here we will come up with the sigma 3.1. So this is the equation, the simplified equation which we will get. Now for block 2, as I mentioned earlier on, that for block 2 here, you can see that sigma 3.2, this sigma 3.2 will be equal to gamma into d. So sigma 3.2 is equal to gamma into d, and sigma 1.2 is equal to sigma 3.2 tangent square 45 plus phi by 2. And if we simply put phi is equal to 0 and this term equal to 1 and this one term equal to 1, so this one will give us the sigma 1.2 equal to sigma 3.2 plus 2c. Okay. Now sigma 1.2 will be equal to q bar because sigma 3.2 is equal to gamma into d or q bar. Now using the equilibrium condition where sigma 3.1 is equal to sigma 1.2, which are the horizontal stresses, so if we put those equations, we will get this equation, and the modified form of this equation would be this one, or we can also write that sigma 1.1 is equal to q bar plus 4c. Now this is an important equation which you can note down. Okay, this equation is important. Now, Q ultimate, because we want to find out the bearing capacity of that soil. It's a very crude example. It's a very simple example that phi is equal to 0, and we are taking and we are finding the bearing capacity of the soil, but it's just creating a base going towards the result is bearing capacity equation. Here, it's the Q bar plus 4C. Now, for the surface footing, if we place on the surface, this Q bar would be equal to 0. Now, in this case, I would say, call that. And Q ultimate would be equal to 4C, and that C is the cohesion of the soil. Now, the lower bound gives us a solution that 4C will be equal to the Q ultimate, or the ultimate bearing capacity of that soil, for the phi equal to 0. Now, similarly, we can also derive an equation based upon, yes, please.
Sir, what do you mean by surface footing?
Surface footing means that if we place the footing on the surface, let me draw here somewhere.
So you will still call it foundation?
Yes, obviously.
On surface.
Yes, obviously. This is the surface here, okay? Now, this is the depth of the footing, and this is the breadth of the footing, and gamma into d would be the, I would call that here, gamma into d would be equal to Q bar. Now, if we place matte foundation, for example, onto the surface, and as I told you, we are just starting with the foundation engineering. We have not find out the, this is a very crude example that only cohesion is playing a role in the foundation. So just to denote that if in case of lower bound solution, okay, let me explain that here as well, that we are having a true failure load. Now, for the true failure load, this one would be greater than the lower bound solution. And this one, true failure load, would be less than the upper bound solution. Do you understand that the value which we are getting here, the true failure value will be less than this upper bound solution and would be greater than the lower bound solution. Now, also, this is the case. Can you imagine the approximation which we are making at this stage? So the solution is saying that just in case if we find out the lower bound solution, so the lowest value which can be obtained for phi equal to 0 and C having some value, this is the lowest possible solution which we can get. Now, what is the lowest possible solution? Q bar plus 4C. And if we even remove this thing, so the Q will be equal to 4C, or the ultimate bearing capacity would be equal to 4C. In this case, if you want to place that on the surface. Now, if you want to place this beneath the surface, this would be equal to 4C. I hope it's clear now.
Yes, sir.
Okay. Now, if we want to find out the upper bound, so we are only interested in finding this ultimate bearing capacity, that what should be the lower bound solution. And now if we assume in another situation that if we are having a foundation here, okay, and this is the surface, ultimate load is applied and some settlement is occurring, and this is the center O, and this is the failure surface, the circular failure surface which is occurring. Here is the undrained shear strength. Here is the Q gamma into D. This is the breadth of the footing, the depth of the footing, the moment arm for the shear strength of the soil. B, d theta is the settlement or the displacement which is occurring. This is the S. Now S you can find out using the S is equal to R theta, or S is equal to B theta, or we can say delta S is equal to B d theta. Okay. Now if we consider the internal work done, and the internal work done by the shear strength of the soil, and in this case phi is equal to 0, so only the undrained cohesion is playing that role. The external work done, that is related to the Q ultimate or the load which is applied on top of that foundation, and Q bar which is related to the gamma into D. If we equate those work done, the internal and external work done, it will give us an expression which is of prime interest to the geotechnical engineer, and that is Q ultimate is equal to Q plus 2 pi Cu, or we can say Q plus 6.28 Cu, or we can say for surface footing that would be equal to 6.28 C. Now here is an important point. So we discussed about the true failure load will be equal, would be less than, would be greater than the 4C and 6.28 C. Can you see what is going on here? The true failure load would be less than the lower bound solution. So this is the lowest value possible, or the lowest bearing capacity value possible, and this is the highest or the upper bound solution, or the upper value, the maximum value possible for the bearing capacity. So this is the bearing capacity. And remember, just to give you again a recall, that we are just making a base that how we can find out the bearing capacities. Now, limit equilibrium method is by far the most commonly used method in stability of the geotechnical structures. And we have seen and we have used this method in landslide slope stability chapter in Geotech 2. Now, same problem here. If we take moments at O equal to 0, and if we solve the same problem using the Q ultimate and the moment arms, the Q bar and the moment arms, the cohesion and the moment arm, then if we introduce shear strength term for the cohesion of the soil, and we solve these equations, so we will come up with the same upper bound solution when the shear strength is equal to the cohesion. And this same term, which is the Q ultimate, will be equal to 6.28 C, and for surface footing, if we place that foundation for the upper bound onto the surface, this will give us the lowest value possible. It's just an estimation, approximation that could be possible, that 6.28 C will give us the upper bound if the foundation is placed on the foundation. Obviously, we are not going to use these in the design, because these are very rough estimation for the time being, but it's just giving you an estimate basis that how the bearing capacity can be find out. Now, if you want to find out the for the surface footing here, so we know that Q ultimate is equal to 6.28 C, and also 4C by, this is the upper bound solution and this is the lower bound solution. You can note down these equations, these are important. Now, if you want to find out the average of the two, so you can simply add 6.28 C plus 4C divided by 2. So you can take the average ultimate bearing capacity for phi is equal to 0 soil, it's 5.14 C. So that's the another value which you can remember is the average value or the average bearing capacity. Here is more detailed and advanced method which is generally used for solving examples and problems, and also finding the bearing capacity of the soil. So Terzaghi developed this formula or theory to find out the bearing capacity of spread footing. Originally it was used for the stripped footing, then later on Terzaghi introduced different shape factors to find out the bearing capacity for different shapes of the shallow foundations. So it's based upon the limit equilibrium method. The D by the depth of the footing is less than or equal to I would say 1, okay, equal to 1. The foundation is rigid and has a rough bottom, so these are the assumptions. The soil is homogeneous, and also the strip footing with the horizontal base, okay, that's an important point. For example, here we are only dealing in this theory, the Terzaghi bearing capacity theory, we are only dealing with the vertical load, okay, and also the surface is leveled. So we are not dealing with the, for example, let me say it's a sloping ground or sloping foundation as well, inclined foundation as well. So this is the case for the Terzaghi's bearing capacity equation, and this is the case, or we will use different inclination factors when we will discuss the Meyerhof bearing capacity equation. Okay. Now, general shear failure mode was assumed in deriving this equation. More Coulomb failure criteria is used for the shear strength of the soil. Now here is the collapse mechanism here. Now AB and J. This is an elastic wedge. We can call that Rankine active zone. Okay, this is the failure mechanism which Terzaghi proposed, and this is kind of a rigid zone. So this is the zone 1, we can call that. This is the zone 2, which is kind of a logarithmic spiral here. Okay, this is logarithmic spiral, and this is called radial shear zone or Prandtl zone. Okay, or we can call that as plastic zone, because the soil, the load is applied onto the foundation here, and this will push the soil in here, and therefore this soil, this is the radial, now this is the linear zone, and that is the passive Rankine passive zone. So the soil is pushed in this way. Please confirm that the voice is clear and the screen is visible.
Yes, sir.
Okay, thank you. Now this is the friction angle here. This is the phi, the internal fraction which we obtained from the direct shear test. This is again phi here. This angle, he proposed that it would be 45 minus phi by 2. This angle also 45 minus phi by 2. Now Terzaghi ignored this portion for the shear strength of the soil, and he ignored this part. Rather, he used this part as a surcharge on top of this failure mechanism. Okay, so you can use this gamma into D. This is the surcharge, and which will also be included in the derivation of the equation. Okay, so we are given with 3 zones: zone 1, zone 2, and zone 3. And similar, this is the half, I would call that as half portion of the foundation on the right side, and similar behavior will also, or similar mechanism will also occur on the left side of this foundation. Here this will be zone 2, this is zone 1, and this is zone 3. This is the elastic wedge, the rigid wedge, which is in active state, which will act, which will move with the foundation. This is the plastic zone here, which is also known as the radial shear zone, and here it is the Rankine passive zone. Now, the free body diagram for the elastic wedge we can also draw. Let me take the greenish one here. Now, if we want to draw the free body diagram, so we already know that Q ultimate is applied on top of this wedge. Here we are given with the friction angle and the friction angle. The weight of the wedge is acting downward, so Q ultimate is acting downward, weight is acting downward. Now the PP, but let's say this is the normal force, is acting onto the side of this wedge. So just to recall here, this wedge is in here, okay, and we are trying to find out the bearing capacity of the soil. If we bring it here, this is the passive pressure, here is the friction angle, again passive pressure on the right side of the wedge, and this angle is friction angle. Now cohesion of the soil would also be acting on both sides of the wedge, so there will be a vertical component for this cohesion as well, so one vertical component up, and I would say 2C, there is another component 2PP, there will be a component of cohesion and a component of passive pressure. Now the height of the wedge can be found out using this equation, h is equal to b by 2 tangent phi. I think that's it. Now if we take the summation of forces in vertical direction equal to 0, and if we equate the forces which are acting downward and upward, is Q ultimate into B plus, so if you go this side, so it will be minus W or 2C, this is the vertical component of the cohesion, and the 2PP which are acting here on each sides of the wall. Now if you want to find out the weight of the wedge, it would be half gamma B into H. Now that H is equal to B by 2 into tangent phi. So the weight of the wedge would be 1 by 4 gamma B square tangent phi. Okay, so this is the B square, I guess, here, which has been left out. Now there is an interesting concept which has been discussed, is related to PP. Now that PP, which is the passive resistance, that is due to the weight of the soil, the cohesion of the soil, the surcharge of the soil. Now where is surcharge? Surcharge is on top of the foundation, like this one here. You can see here is the surcharge, cohesion, the cohesion in the soil, and also the weight of the soil will also give us an ultimate. So it's just giving us an idea that what are the factors which Terzaghi is considering in deriving the Terzaghi's bearing capacity equation. Now we are solving for this Q ultimate. Now we are relating these weights, the unit weights. Can you see those terms which you obtained in Geotech 1? So here your all effort of the Geotech 1 and Geotech 2 can be seen and can be practically utilized in finding the bearing capacity of the soil. And the PP concept which you understood in the Geotech 2, the friction angle, how you determined, how you obtain the unit weight of the soil. So these are the parameters which are used. So Terzaghi assumed that the PP is dependent upon these three terms: the weight of the soil, the cohesion of the soil, and the surcharge which is acting on the soil as well. But it's difficult to solve this problem because it's an indeterminate problem. So he came up with a solution that, for example, if we are using PP in this equation, this one, okay, let me clear this a bit. So he called that equation as equation A. Okay. Now this PP is dependent upon the weight of the soil, cohesion, and the Q, which is the surcharge. Now he evaluated PP, that PP is equal to PPC, which is the cohesion. Now in that case, PP gamma will be equal to 0, PPQ, which is due to surcharge, equal to 0. Then he put the value of PP as PP gamma, and in that case the cohesion of the soil he assumed equal to 0, and also the unit weight, sorry, the surcharge equal to 0, because he's using the unit weight PP, and the PP is equal to PPQ, which is due to the surcharge. Now that passive resistance which is occurring due to the cohesion equal to 0, and also due to the unit weight equal to 0. So these were the three scenarios which he used in further derivation of the ultimate bearing capacity of the soil for the C and phi condition. Okay. Now there is a lengthy derivation here, and Chairman Saab has intentionally removed that part in here. But if you put the values of those PP gamma, PP C, PP Q, then you will obtain a final equation for a strip footing, which will consider C and C, which is related to the cohesion of the soil, Q and Q, which is related to the surcharge of the soil which is acted on top of the soil, and also the weight of the soil will also contribute to the bearing capacity of C and phi soil. So you can clearly see that the effect of cohesion and friction can be seen. Now, how and where we are going to see those cohesion and friction? NC, NQ, and N gamma are bearing capacity factors which are dependent upon the friction angle of the soil. Now, in order to account for different shapes of foundations, for example, there are different shape factors Terzaghi introduced. For example, for strip footing, it's okay to use 1. For the rounded footing, 1.6. So he performed lots of model tests there, and he came up with these values from the lab test and from the analytical methods. Then for the square, so you can use SC and S gamma in this equation. For example, this one, here it's this one. For the square, this one. For the square S gamma would be here, then for the rectangular one, and also for the S gamma here. Now, yes, please.
Sir, can you explain this passive pressure a bit more? Because, sir, we haven't talked about it before in Geotech 2 or anywhere else.
Oh, passive pressure.
Sir,
How about the retaining wall?
Oh, okay.
Who taught you? Who taught you the? Who taught you the Geotech 2? Me
Sir,
or?
yes, sir, we studied it. I got confused a bit. Is this
Okay,
the same
I will go
passive
about
pressure?
that. No worries. don't know. I thought maybe we have discussed that, but
Sir,
I
we
will
studied
briefly
it,
go.
but in retaining walls only.
Yes, this is the same thing, you know. So if there is a retaining wall here, for example, here, and this is the upstream side, and this is downstream side, I would call that. And then if that wall is moving away from the backfill material, so this soil is in active condition, and there is a pressure which will be applied because the wall tries to move into the soil, and this soil will exert a pressure which will be the passive pressure. So this is the same pressure which we studied in Geotech 2 for
But
the
sir, there
retaining
we
walls.
only studied
Okay.
it. There we only studied it in retaining walls, sir.
Yes, exactly. Yep. So the same passive pressure and the same concept he took from the retaining wall, and that's why we call that PP, and that PP was also mentioned in this zone is the Rankine passive resistance zone. Okay.
Okay.
And this zone he named that as the Rankine active zone. So, and his friend, because the originally he took the work from Prandtl, this zone he also called in some textbooks he has mentioned this radial shear zone as the Prandtl zone. So he proposed that in 1950s, and after a few years, Terzaghi is proposing this theory. So that's why he is naming as Prandtl zone as well. So these are basically related to the different names of the researcher as well, and the work they have done. Okay. Now, for different shapes of the retaining wall, now the next question will raise in our mind that how we can find out the bearing capacity factors. Now, how we can find out the bearing capacity factors for example, if we are given with the friction angle, usually in exams, in assignments and problems, the figure is given, and then you find out the bearing capacity factors, for example, the NC, NQ, and N gamma, the bearing capacity factors. Okay, so for example, if we are given with the friction angle of 30°, please give me NC, NQ, and N gamma values. For friction angle phi 30°, I would like to request NC, NQ, and N gamma values.
Sir, NC would be around 38 something.
Okay, let me write down that. Okay, 38. If someone disagree with the value, okay, NQ. NQ.
Sir, it would
NQ.
be around 24.
22, 24, हाँ sir.
Okay, 22. No problem. Okay. Now, N gamma.
19.
Okay, so if we move from 30 here, so it's 20, 30, and 40 here. So yeah, you are right. Approximately 38. That's good. I'm okay if you're using the 38 value or even 40 or 36 as well. So let's go for this one. It's 2024. Okay, I'm okay with these two values if you're using in the bearing capacity equations. Now the third one would be approximately 1920. Okay, good. Excellent. Now a table is given, and these are the highlighted values which we will use in examples and problems. So usually the figure is given to find out, to give just an idea that how we can find out these values. Now, as you can see that the Q ultimate, can we find out the C and C plus Q and Q plus half gamma B into N gamma. There are unit weight term which is used in the, I would call that third term, okay? And there is also gamma into D, if you remember, that is the second term. So based upon the location, this is the case 1, case 2, case 3, case 4, and case 5. So if the water table is at the ground surface, then for example, if we draw this figure here, here is the ground level. So this is the case 1. Now if in the case 1, so how it's gonna change the value of the and C plus gamma into D and Q plus half gamma B and gamma. Okay, so what do you think about the unit weights? For example, if this is the first term, the second term, and this is the second term gamma, and this is the third term gamma. Okay, so this is the third term, and so we are going to use the gamma prime, which is gamma saturated minus gamma of water. This is the gamma of water, and here this one is also affected, so we are going to in gamma of water. Agree?
Yes, sir.
Similarly, for another case as well, so if the water table is here, so this one will not be affected, so we will use the gamma total or gamma bulk, and here this term is affected. Now we are going to use the gamma prime gamma saturated minus gamma of water. Okay, now we will come here and we will see, so that is the unit weight which is equal to gamma total or gamma bulk, and for the third term we are going to use this one. Now what water table below the wedge, it means that we are so if you remember, please confirm that you can hear me. Please confirm that you can hear me.
Sir, we can hear you
Yes,
now.
sir. We can hear you.
I don't know, the signals dropped
Yes, sir, it
here.
dropped for a couple of seconds.
Okay. Okay, it was just for a few seconds. That is good. Yeah. Okay. So here, you can see the height of the wedge. We can find out using h is equal to b by 2 tangent 45 plus phi by 2, and that phi is the friction angle.
आपकी आवाज नहीं आ रही.
अच्छा नहीं आ रही?
आ रही है सर आपकी आवाज.
Okay. Okay, thank you very much. It's almost, I'm trying to explain, those different cases there. It's almost done. So just hold on for a few seconds and few minutes. So hopefully we will finish the water table effect here. So you can clearly see that how the second term and the third term is affected by the water table. Depending upon the location of this water table, these two terms will be affected. And then if it's at the base of the footing, water table below the wedge. Now this is important because you can clearly see if the water table is below the wedge, these two terms won't be affected. Okay, and for confirmation of this water table below the wedge, we need to use this equation in solving the problems. So please write down, this is a very important equation which you need to write, okay, which is also used in the problems and examples as well. So we will go here now. This is the v by 2 plus, sorry, this is plus, okay, this is the plus v by 2. Now if the water table is here, that's case number I guess 3, and the case number 4 is if it's here. Okay, this is the case number 4. This is the D1, D2, and here is the D, and case number 5 will be in mid of this wedge here, and here is the ZW, depth of the water table. What else we need in here? H is the height of the wedge, and that is the depth of water table. Gamma submerged is equal to gamma saturated minus gamma W. Okay, this is also given here. So that's how we can use and modify the different terms in the bearing capacity equation. But for the today's important equation, this is the Tazari's bearing capacity equation, which we will be, or the benchmark equation. I would call that as a benchmark equation for finding the bearing capacity of the soil. So Tazari started with this equation. Now, then he added the shape factors. Then Merhoff will come, and he also introduced the water table effect. And now the Merhoff will come, and he will introduce several other parameters and factors like the inclination factors, the depth factors as well, just to give depth to the to obtain, to extend this equation for more realistic cases which can be used in practically in the field. So thank you very much for listening very patiently. We will move towards our question and answer session now. If you want to ask any question, you can ask.
Yes, sir. Sir, will we be using this Tarzani equation only?